Hi, so in this video we will be talking about merge sort, which is a very popular sorting technique. So let us understand the concept of merge sort and then we will implement merge sort to sort a unsorted array. So let's go through the steps involved in merge sort. So let's say given an input array which is like this 10, 5, 2 and we have 0, 7, 6, 4. So this was the input array given to us, and what merge sort says is we have three simple steps. The first step is you divide the array in two parts. Okay, since it is a divide and conquer algorithm, you divide the array in two parts and you divide this array about the midpoint. Okay, so maybe this is one part and let's say this is another part. Okay, we have 10, 5, 2 and we have 0, 7, 6, 4 as the second part of the array. Okay, so this is my input array. And what we do next, we say okay, we are going to recursively sort the left part and the right part. So let's say this is the left part and this is the right part. We are going to use the same merge sort function to sort these two parts, and it's going to be a recursive algorithm. So we can say okay, merge sort left and merge sort right. Okay, merge sort right. This is what we actually do. So maybe this array is from starting S till end. So we divide this about mid. So left part is from S to mid and the right part is from mid plus 1 till the end. Okay, so this is what we have in the right part. Now what is the next step? Once you get these two arrays as sorted arrays, we will see how these arrays get sorted recursively when I will do the dry run along with the code. But let us assume as of now that our recursive function works and it gives us the sorted arrays, and you get 2, 5, 10 here and you get 0, 4, 7, 6 and 7 here. Okay, so let us assume that you get these two sorted arrays after calling merge sort on the left part and the right part. Now what is the final step? The final step is we just need to merge them into a single sorted array. Okay, so that is the final step of this merge sort method. We have to merge the left and the right parts in the single array. So let us try to merge them. Now this is an important method. How do we merge? Okay, so we basically keep two pointers. Let us say I pointer here and the j pointer here, and maybe we are creating a temporary array from where we will copy back all the elements to the original array. So we keep a k pointer here. Okay, so we make a comparison. We say okay, between 2 and 0 which element is smaller. So we know that 0 is smaller, so we put 0 here. J moves forward. Between 2 and 4 which is smaller? 2 is smaller, we put a 2 here, and uh, this moves forward. Between 4 and 5, 4 is smaller, 4 moves forward. Between 5 and 6 we have 5, and between 10 and 6 we obviously have 6. Between 10 and 7 we obviously have 10, and now this part of the array is left. Okay, so what we do, whatever elements are remaining, we just copy them directly in the temporary array. Okay, so once we have this temporary array created, we put back all the elements back in the original array. Okay, so these elements are copied back to the original array and you will get the sorted array. So this is how merge sort works, and you can see it's a very simple DNC algorithm. Okay, it's a very simple divide and conquer algorithm. Okay, so now more details we will discuss in the implementation part when we will write the code, and then we will try to dry run the exact code. Okay, each and every step. So let's see the implementation in the next part. Hi everyone, so let us start implementing the merge sort method that we have just discussed. So we have this merge sort function that takes input a vector and start and end points of the vector that we need to sort, and we are going to complete this one. Okay, so let's see how we can do it. So first thing is we need to write a base case. Okay, since it is a recursive method, you need to figure out what is the smallest possible array which will not require sorting. Okay, and here you will have the recursive case. So in the base case, you can say if start is greater than equal to end, that means we don't have any elements, or we just have one element that we need to sort, we can return, because array containing one element, we can assume this is a sorted array. In the recursive case, we will find out the midpoint. We can say start plus end by 2, and then we can say okay, merge sort on the left part of the array, that is array start and mid, and we can say merge sort on the right part of the array, that is array mid plus 1 and end. Okay, and once the left part and the right part are sorted, what do you need to do? You need to combine them into a single array. Okay, so you can say return merge array start and end. So we will write this function, as you can see here. We will write this function that merges two arrays into a single array. So as of now, we are accepting a one array here, but let us assume we can break this array here and we will merge it. Okay, so what we discussed, let us say we have this entire array that is now divided into two parts about mid. Okay, so one part will start from mid plus 1 and another part will start from s, and this entire array is from s to e. So this is one part from start to mid, and from mid plus 1 to end, this is another part of the array, right? So we need to combine them into a new vector, you can say. We will create a new temporary vector and we will try to compare elements from these two parts, and we will try to fill this vector accordingly, right? So let me say we have a variable I that points to start, we have a variable mid that is s plus e by 2, and we have j that starts from mid plus 1. Okay, we have I here, we have j here, right? Okay. So we also create a temporary array, so vector of integers temp, and what we need to do, we need to say okay, while I is less than equal to m and j is less than equal to e. So while we have elements from both the parts to compare, we can compare them. So if array of I is less than array of j, then in the temporary vector I will push back the element from the first part of the array, that is array of I, and I can also do I plus plus. Otherwise I will push the element in the temporary vector from the second array, that is array of j, and I can increment the j pointer j plus plus. Okay, now this loop will break when one of these arrays is exhausted. Okay, maybe you have 2 4 6 here, and maybe you have 0 10 12 here. Okay, what will happen? So this, in the beginning you will have a 0 here, then you will put all the elements 2 4 6 from here, and this loop will be over because I has reached mid. Okay, so your I variable has reached mid and you don't have any more elements in this array which you can compare with the remaining elements of this array. So what you need to do, you need to copy back the remaining elements directly. Okay, so there would be two cases, either you can have remaining elements in the left array or you can have remaining elements in the right array. So we will write code for both of them. Okay, so copy remaining elements from first array or copy remaining elements from second array. Okay, or the second part. So let us say, so we can say while I is less than m, while I is less than equal to m, we can say temp dot pushback array of I, and we can do I plus plus, or we can copy from the second array. So while j is less than equals to end, we can say temp dot pushback array of j and j plus plus. Okay, so in any of the cases only one of these while loops will work. Okay, out of these two loops only one will execute, because one of the condition will automatically become false when this while loop stops. Okay, So finally we need to copy back the elements from temp to our original array so that our merge sort function can see the actual changes. Okay, our merge sort function does not know anything about the temp array, so we need to copy back all the elements to the original array. So we are going to iterate from k equal to 0. Okay, so in the temp array the indexing will always start from 0, but in the original array the indexing will be from s to e. Okay, so maybe you make a recursive call on this part of the array. Okay, then this part is s, this part is e, it is not 0 to end. Okay, so we can say, okay, for int some index that is starting from s, index is less than equal to e, index plus plus, we can say in the original array, that is array, so we are passing this array by reference. Okay, so that the changes can get reflected. At array of index we can put temp of k, and in the temp array we can say the k starts from 0, because we are always creating a new temp array whenever this function is getting called. So, and we can say temp of k plus plus, so this k pointer also moves forward, and that's it. We can have the return statement here. Okay, so we have this thing as arr, and maybe this thing as arr. Now let us try to run our code and see the output, and you can see we are getting this array which is now a sorted array, right? So that means our merge sort function is working perfectly fine, and also our merge function is also working fine, right? So it's little big, but you can say it's not difficult. So this is the entire merge function that we have, right? Now if you want, I can just dry run the code once more, and that will make the things more clear to you how recursion works in case of a merge sort. So let us dive little deep and see how the recursive solution works. So we have this array, we have 10, 5, 2, 0, 7, 6, 4. So you break this into two parts. So you create one part 10, 5, 2, and you make this call at line number 51. Okay, so line number 52 will not execute till this array is not sorted. So we again are in the merge sort function, a new merge sort function is called. You again break this into two parts. So you say, okay, let's say this is one part. Okay. So I think with the logic we have written, this will be one part and this will be another part. Okay, so we have 10, 5, 2 and 0. So we break this into two parts. We have 10 and 5, and 2 and 0 will be executed later on. Okay, so we again break this into two parts. We have 10 and we have 5. Now what happens? We say the start and end are equal. So we are in the base case and we return. So we just return these two elements. So when this merge sort is called, we break this into two parts, 10 and 5. Now what happens is we make a merge sort call on this part that hits the base case and we return. You make a merge sort call on this part that hits the base case and returns. So when we return in this particular function, right? So it was like this: merge sort with the array containing 7 elements, with the merge sort an array containing 4 elements. You create a merge sort call with an array containing 2 elements. You create a merge sort call with an array containing 1 element. This call returns back, and this call also returns back. Okay, so this call goes off. You again make this call for 5, and you are again back in this call. So now you have 2 elements and you already made these two calls, so you merge them. So when you merge them, you get this array 5 and 10. Okay, and this goes back. Okay, this goes back. So this part basically knows the left part has now been sorted, so you make a call on the right part to sort it. So you make a call here, so it becomes 2 and 0, and both of them return. And when you are coming back, you basically try to merge these two arrays and you basically get 0 and 2. Okay, and once you get the left part and you get the right part, you are in this merge function in which you had a merge sort function in which you had 4 elements and you have already sorted the left part and the right part. So what happens? This merge sort 4 function basically now calls the merge routine and it tries to merge both of them. So you get 0, 2, 5 and 10. Now you are in this merge 7 function in which you have already sorted the left part of the array and you make a call on the right part of the array. So this ms4 goes off and merge sort 3 is called. Okay, so where you have these 3 elements of the array that you need to sort. So you have 7, 6, 4. You again break them into 2 parts, 7 and 6, and you have a 4 here. And then you again break them into like 7 and 6, and they are merged like 6 and 7, and you know this part is now merged, the left part, and the right part is already sorted because you have one element, so this returns from the base case. And when you merge it with this part, it becomes 4, 6 and 7. Okay, and now you are again in the merge sort 7 function where you have the left part which is sorted, the right part which is sorted, and you merge them. So you have now 0, 2, 4, 5, 6, 7 and 10. So this is your final output and this is now returned to the main method. Okay, so I just try to show you with the help of call stack and the entire recursion tree. The only thing you need to remember is recursion works in a depth first manner. Okay, so these calls don't happen parallelly. Once you go deep inside a branch, once that branch is finished, then you backtrack and you go in the another branch. Okay, so this is how the recursion works. Okay, so you go like this. So that's all for this video, and I hope you really understood the merge sort sorting algorithm. Thanks a lot. Hi everyone, so in this lecture we will be talking about quicksort, which is again a very popular sorting algorithm. So let's see how quicksort works. So we will discuss the concept and the implementation of quicksort to sort a given array or a vector. So a quicksort is a divide and conquer algorithm. Okay, so what we'll see, given an input array which is unsorted, it will help us to sort this array, and its average case time complexity is order of n log n, and in the worst case it can take up to order n square time. But yeah, it's one of the very popular sorting algorithms you must learn, right? So let's see how this algorithm works. Okay, so one thing to remember about this is it's a divide and conquer algorithm. Okay, similar to merge sort. What this algorithm does, in the first step it chooses a pivot. Okay, so you have to choose a pivot point. Okay, so a pivot point is a point about which you're going to divide your array. Okay, let's say this can be either the first element, or it can be the last element, or it can be any random element in the array. So for our example, we are just going to pick last element of the array as a pivot always. Okay, so whatever the array is given to us, we will pick the last element as a pivot element. Okay, the next step is a partition step. It's the most important part of the quicksort. So what in this step, what do, you try to partition your array into 2 parts. Okay, so what you will do, you will make you will say, okay, I have a 4, I will put all the elements which are less than 4 in one part and all the elements which are greater than 4 in another part, and 4 will be in the correct position. Okay, 4 will be in the correct position. So if I just see what elements are less than 4 in this array, so we have the elements 2 and 0, these are less than 4, and all other elements 5, 10, 7 and 6, 5, 10, 7 and 6, they are greater than 4. So we will put all of them in another part. So we'll see how to write this method. Okay, so once you have this, you recursively sort the left and the right part. Okay, you have to recursively sort the left part of the array. This is the left part and this is the right part. Okay, so the 2 partitions that you have created, you can recursively sort them. Okay, so recursively sort by, I mean, you again call the quicksort method to sort all of these elements. So if you sort these 2 parts recursively, what you will get 0 2 in the left part, then you will have 4 in the right part, and you also sort the right part, you will get 5 6 7 and 10. So this is how you can see you will get a sorted array. Now let me explain this partition method in more detail before we dive into the implementation. So these are the three important steps of quicksort, right? And since we are going to use recursion to implement this algorithm, you can also have a base case. If your array contains only 1 or a 0 elements, so you can simply return. If you have 1 or 0 elements, you can return from that part, okay? So that will form your base case if you're using recursion, right? So let's see how this algorithm is going to work on this particular example. So in the beginning, I will say, okay, let me keep 4 as a pivot element. So let's say this is pivot element, and now I'm going to explain you how you will partition your array, okay? How to partition your array into two parts. So there can be multiple ways to write the partition algorithm. So there is a popular way to write this algorithm. It is also mentioned in the CLRS book. That is a very popular book for algorithms. So I'm just going to refer that method, and I'm going to explain you how it works, right? So the idea here is you have to divide this part into two parts, okay? You have to divide this unsorted array into two parts. Maybe let me say this is one part, this is, let's say, unsorted part. Sorry, this is yeah, the entire part will be unsorted, but let us say we are dividing into two parts. The first part contains all the elements which are less, and the next part contains all the elements which are greater than pivot, okay? So we all these comparisons we are making with comparison to the pivot element, okay? That in case is 4, right? So what we will do, I'll say, okay, in the beginning I have I will keep a pointer here, okay? I will say, okay, so I will denote the end of the first part, and J will denote the element that we are currently processing, okay? So it will be one larger than this particular index, okay? Whatever index is this, J would be one larger than it, okay? So in the beginning, I is at, let's say, -1 and J is at 0. So what we will do, we will compare, we will iterate from left to right, and we will compare whether 10 is smaller than 4 or it is greater than 4. So what we came to know that 10 is greater than 4. So what we will do, we will say, okay, I will not move, but J will move, okay? So we have processed 10. So J comes here. So we come to 5. Is 5 greater than 4? Yes. So we will not do anything. We will just move our J pointer to the next location. So J is now standing at 2. Is 2 greater than 4? The answer is no. Okay, so if it is not, what we will do, we will expand this window. Okay, so we are creating two types of windows or partitions, you can say. We will try to expand this window. Now you may ask, how do we add 2 in this window, right? So answer is very simple. You basically swap 2 with the I plus 1th index, okay? So, or you can say I will come to this index now, and we can do the swap operation. So after swapping, you will get something like this. You will have 2, 5 and 10, okay? And I is pointing at this index and J is pointing at this index, okay? So at this particular index, now you have a 0, so which is again smaller than 4, right? So you again do the same step. You say, okay, I will do I plus plus, and then I will swap these two elements, okay? So I comes here and you do the swapping operation, okay? So it will become something like this. You will have 2 followed by 0 followed by 10 followed by 5. So basically we are trying to swap these two elements, okay? And now J is at this particular index, and here you have this element 7, which is greater. You don't do anything, okay? So this is your first partition and this is your second partition, and then J is at 6, which is again greater than 4. You don't do anything, and finally we are finished, okay? So this is the final state of the array after calling the partition function, okay? So let me just draw it again. So it will look something like this: 2 0 10 5 7 6, okay? So all of these elements, as I said, these elements are greater and these elements are smaller than the pivot element, and here we have this pivot element 4. So we have one more step in the pivot function. We have to do a final swapping. So let's say this index is now I, and this index is j, and this index is the pivot index, which was the last element of our array. So we can simply say you just swap array of I plus 1 with the array of pivot. Okay, so this will actually place the pivot element in its correct position. So we will place pivot element in the correct position. Okay, so what will happen, 4 will come here and 10 will go here. So let me just draw this array now. It will become 2 0 4, and we will have 5 7 6 and 10. So this is how the array will look like after the first partition function call. Next time what you need to do, you need to call quicksort on this part of the array, and you need to call quicksort on this part of the array. So how it will work, it will say, okay, let me take 0 as the pivot element and let me try to partition this part of the array. So here we have only one element which is greater than 0. So 0 will come in its correct index and 2 will come here. So you will get 0 comma 2 by making a recursive call on this part, and you will also have a 4 here, and you will also make a recursive call on this part of the array. You will say 10 is a pivot, and this will become the smaller part of the array. And how it will work, all the elements are smaller, so you will have 10 in its correct place, and you will make a quick sort on left part of array. Okay, so left part is 5 7 6. You will say, okay, let me take 6 as a pivot and do the work again. So you don't have what you will have if you just make a recursive call on this part of the array. Okay, so how it will work, it will take 6 as the pivot, and then you will try to partition. It will become 5 6 and 7. Okay, and you will have a 10 here, and you will have a 4 here, and 0 and 2 here, right? So by making recursive calls, okay, by dividing the problem further and further, we can actually sort this array, something similar to merge sort. So I hope you really understood the quicksort algorithm, and in the next video we will discuss the implementation. Hi everyone, so we have seen the quicksort sorting algorithm, and now we are going to carry forward the similar idea for solving a searching problem. Okay, we have done sorting, now we are going to do searching using the idea of partition given by quicksort. So the problem that we are going to take is called as quick select, and it says given an array you need to write a function that takes input an array of distinct integers, and it returns the kth smallest element of the array. So for example, this is the array given to you, and what would be the kth smallest element? Okay, so obviously the first approach that comes into mind is do the sorting and find the kth smallest element, or maybe use a heap and find the kth smallest element. Okay, so let's see how we can solve this problem using this quick select idea, right? So we have this array. So after sorting, the array would look something like this: 0 2 4 5 6 7 and 10. And I'm saying, okay, what is the fourth smallest element? So we have first, second, third and fourth, and the fourth smallest element is going to be 5. So now obviously we need to build a solution that performs better than sorting in average case. Okay, so this is the input. So let us see, if we try to do something like a quick sort, if we do something like a partition function, what will happen on this array. So let's say we call the partition method that we discussed in the quicksort function as well. So what this partition method does, it tries to partition this array about a pivot element, and it also gives us what is the index of this pivot element in linear time. So what we will do, we will have, maybe we will place 4 in its correct position, and we will have maybe 2 and 0 here, and we will have maybe 5 7 10 and 6. So these elements will be unsorted, these elements will be unsorted. Okay, so I'm not written them in correct order, they would be some random order that we have to calculate. Okay, but we just know that this element is in its correct position, and let's say this position is 3. Okay, and what is the position you're trying to look at? So you are looking for an element which is at the 4th position. Okay, So in quicksort, we did one thing. We made a quicksort call on both the sides, on the left part and on the right part, to sort the array, right? But in this case, we don't need the entire array to be sorted. We can simply say we will discard the left part because we want to save time, and we can just make a call on the right part of the array because k is greater than pivot. Okay, so that means if the third element is lying at this index, the larger element will obviously it will lie on the right. So we will either go left or we will go right, but we will not go in the both of these directions. Okay, so this is the idea, and that will help us to optimize this solution, right? So now what happens, we come to this part of the array and we say, okay, give us the pivot. So now maybe this is the pivot, and we try to place 6 in its correct index. So maybe 6 comes here, and we have 7 and 10 here, and we have a 5 here, and we came to know that, okay, this element is not at the this element is at the 5th position. This element is at, so we can see this p is 5 and the position that we need to figure out is 4. So what we will do, we will discard the right part of the array and we will make a call on the left part. Okay, so once we make call on 5, we will get p equal to 4, which is same as k, and we will return this element and we can see output will be 5. Okay, so this is the whole idea of quick select algorithm, and I will give you one homework for the same. You need to figure out what is the worst case complexity of this algorithm and what is the average case complexity of this algorithm. Okay, so it's a pretty interesting problem to solve, so do work on it, and it's a part of assignment. Okay, so that's all for this video. See you guys with the implementation in the next video. Hi everyone, so let's start implementing the quick select algorithm. So what we will do, we have this function which gets the vector and the starting and the ending point, and we get k, the kth smallest element that we need to figure out. So we also have a partition function that is coming from the quicksort method that we have already implemented. So we are just going to use that directly. So first step is we will do the partition. We will say, okay, partition this array and give us the index of the pivot element. Okay, and once we know the index of the pivot element, we can compare with k. If this is equal to k, then that means we found out our element. So we can say return array of p. But if it is if k is less than p, okay, so that means we need to make a call on the left side. So we can say return quick select array start p minus 1 and k, and if k is greater than p, then we have to return this function from the right side. Okay, so starting from p plus 1 till end and k. So that's it. Okay, so now let us test our code, and I'm assuming that yeah, so that k will be inside the array. Okay, so we are not searching for any random element, we are just saying we are searching for the second smallest element or the third smallest element. So basically k should be less than n, right? That's the whole idea. So yeah, so we have to create this as this, and build is successful. Now we can actually do the searching. So dot slash quick select, and okay, we have printed array dot size that we can remove, and maybe the first smallest element, that is 2. So in this case I'm taking 0 based indexing. If you want, you can take 1 based indexing as well. So the 0th smallest element, you can say it is 0, that's fine. The first smallest element is 2, that's fine. The second smallest element, that is 4. The third smallest element is 5. The fourth smallest element is 6. The fifth smallest element is 7, and the sixth smallest element is 10. So you can see our algorithm is working fine for all values of k, And this is how easy the code is. You just need to compare your k with the value of the pivot index that you're getting from the partition function. Okay, so that's all. See you in the next part. Hi, so let's discuss another interesting problem. It's called as inversion count. So let me go through the problem statement. It says, given an array containing integers, you need to count the total number of inversions. Okay, so we need to understand what is an inversion. So two elements of the array form an inversion if ai is greater than aj for I less than j. Okay, for example, in this array, if I count how many inversions I have. Okay, so let me show you one sample inversion. So maybe 2 and 1 will form an inversion because 2 is greater than 1 and index of 2, that is I, is less than index of 1. Okay, so all such pairs will form a inversion. So let us see how many inversions do we have in this array. So 0 will not form any inversion. 5, so do we have an element which is less than 5 and which is coming after 5? Yes, 5 will form an inversion pair with 2, with 3 and with 1. Okay, so 5 will form 3 inversions. How many inversions 2 will form? 2 will not form an inversion with 3, it will form an inversion with 1. So 2 comma 1 is an inversion about 3, and 3 will also form an inversion 3 comma 1. So you can see we have 5 such pairs and we have sample output as 5. So this is the meaning of the question. Okay, so we are given an array, we need to find out how many inversions do we have. So clearly we can have a brute force approach in which we are comparing every element I with all the elements which are coming after it. Okay, so for 0 you iterate this much, for 5 you iterate this much. So this will obviously take order of n square time, and we want to do something better than it. Okay, so if you just consider all pairs, okay, for all pairs I and j that lie in this array, we can check if they form an inversion. We can increment count plus equals to 1 if they form an inversion, otherwise we don't increment the count. Okay, so that is one thing we can actually do, but we do want to optimize this solution further, right? So let us dive deep in and see how this can be actually solved. Okay, so the idea is instead of counting each pair, right, so if we just come to know, if we somehow calculate directly how many inversions each element will form. Okay, how many inversions each element will form. Okay, each element will form. So this question we need to approach in a different manner. Okay, so let's see. So let us try to apply some DNC algorithm, something like a merge sort. Okay, and we will come to know that if we perform something like a merge sort, we will come to know that how many inversions each element will form. Okay, so it's a bit tricky, not so straightforward, I would say. Let us try to divide this problem into two parts. We will say, okay, let us apply a divide and conquer algorithm. Let's say this is the one part, or maybe let us say this is one part. Okay, and this is another part of the array. So if we just say, okay, we will apply some DNC algorithm, so what will be the answer? What will be the number of inversions? So it will be the number of inversions in this part. Okay, let's say C1, number of inversions in this part, that is C2, plus there would be some inversions which would be cross. Okay, which would be in which one element lies in this part and another element lies in this part. Okay, so let us see what are the inversions in C1. So in C1 we have inversion 5 comma 2. Okay, what are the inversions in C2? So C2 basically means both the elements lie in this part of the array. So 3 comma 1 is an inversion. Okay, and what are cross inversions? What are cross inversions? I just call it as, let's say, CI. So cross inversion basically means those inversions in which one element lies in one part of the array and the other element lies in the other part of the array. So they are 5 3, there we have 5 comma 1, and we also have 2 comma 1. That's also one more inversion that we have. So if we just see what is the total inversion, so that is nothing but total is number of inversions in this part of the array C1 plus the number of inversions in this part of the array C2 plus the cross inversions. Okay, so it is again 1 plus 1 plus 3, that is 5. Now we figured out how we can solve this problem using a divide and conquer algorithm, and we are quite sure that this will help us to reduce complexity than a brute force solution, right? Now let us try to further analyze how do we solve this. Okay, how do we compute cross inversions? Okay, so how do we calculate C1? So if we have a function, let's say we have a recursive function int count inversions, and that takes input a array start and end. So if we just call this function on the left part, it will give us C1. Okay, if we just call this function on the right part, it will also give us the inversions in this part of the array. But what about cross inversions? Okay, how do we calculate cross inversions? That is the most tricky thing to do in this particular problem. So now let us focus on this part. So let me start again. So what I'm going to do, I'm going to use something like a merge sort. I will say, okay, let's divide this array in two parts. This is one part, this is another part, and we will actually perform merge sort on it. Okay, we have 0, 5, 2 here, and while doing merge sort, we will compute how many inversions do we have. So we have this thing and we have this thing. So 0, 5, 2 and 3, 1. So we will break it further. We will break it into 0, 5, and we will break it into 2, and we will break this into 3, and we will break this into 1. We'll break this into 0, and we'll break this into 5. Now you may ask, okay, what next? The next step is we need to do the merging. Okay, so what we will do, we'll merge 0 and 5. Okay, so they will get merged and they will be placed here, but I'm just drawing here so that I don't overwrite my original drawing. So 0 and 5. So okay, so while merging we can see will 0 and 5 will form an inversion? The answer is no. 0 is coming before 5 and 0 is less than 5. So we will have a 0 here and we will have a 5 here. Now what is the next step? We need to merge 0, 5 along with 2, and during this merge process we will count the cross inversions as well. Okay, so what is going to be a cross inversion here? So when you are going to compare 0 and 2, so which one is smaller? So obviously 0 is smaller. Okay, so we have a 0 here. Now between 2 and 5, which one is smaller? Obviously 2 is smaller, right? Now you can see that 2 is going to a place, okay, which is before 5. That means 2 is going to form an inversion with all elements which are greater than equal to 5. So this is a very important statement. Okay, so I'm going to place a 2 here, and I'm going to count how many inversions this 2 is going to form. The answer is 1, because 2 is greater than equal to one element, that is 5. So we place a 2 here, and finally we place a 5 here. So for this part we get our answer that 2 is going to form one inversion, 0 is going to form 0 inversions, 5 is going to form 0 inversions. We get the answer as 2 plus 1 plus 0, sorry, 0 plus 1 plus 0, that is 1. And this is what we have seen in this part of the array that we called as C1. We got one inversion. Okay, that is fine. Now let us try to merge these two parts of the array. Let us try to merge these two parts of the array. So now we have 3 and we have 1, and you can see when we are going to merge, when we are going to take an element from the right, okay, that means it is bigger than this element, and this element is coming before than this element. So whenever we have such a case, when we have an element at the right that is bigger than some of the elements on the left, then suppose you had maybe 3, 8, 7 here. Okay, so I'm just giving you one example here. Suppose you had something like this: 0, 3, 8 and 10, and here you had maybe 1 and 12. So when you're going to merge these two arrays, you will first take 0. It will not form any inversion. It will say we have 0 inversions. But when you're going to compare 3 and 1, what you're going to do? You're going to say 1 is bigger than 3, and one is also, sorry, one is smaller than 3 and one is also smaller than all elements which are greater than 3. So that how many inversions one is going to form? One is going to form 1, 2, 3 inversions. So we put a 1 here, but in our inversion count we will increment 3. Why? Because let's say this index is mid, this is I. So how many elements we will have? So we will have mid minus I plus 1 inversions. These many inversions we are going to add in our count. So this we will see in the code as well. This is a very important step. When you get an element from the right that is bigger than the element from the left, that means that element is smaller than the element from the left. So it means one is also smaller than 8 and one is also smaller than 10. Okay, so this is the whole idea. That's why we add 3 to our inversion count. Next, what we are going to do, we are going to compare 8 and 12. 8 is smaller, we don't add anything. Then we are going to have 10, we don't add anything. Then we are going to add 12, we are not going to add anything. So we will get 0, 0, 0. We will have 0 plus 0, 0. So we are calculating inversions while merging. Okay, we are calculating inversions while merging. Now you can see we are merging 1 and 3. So 1 is smaller than 3, and how many elements we have greater than equal to 3 in the left part? We have only one element. So we will add 1 to an inversion count and we will put the element 1 here, and this array is over, we will put 3 here. So similarly in the right part, that was our C2. We say okay, C2 is also 1 because of this thing, 0 plus 1, 0. Now the final step is we need to merge these two arrays. We need to merge these two arrays, and again we need to count how many cross inversions we have. Okay, so let us make another array of 5 elements, and now we have 0 and we have 1. We copy the element from the left, we add 0 to our inversion count, and then we have 2 and 1. Now 1 is smaller than 2, so that means 1 is also smaller than 5. So whatever elements we have here, that will be added to our inversion count. So we have 2 elements which are greater than equal to 2. So we put a 1 here, but we add 2 to our inversion count. Then we have comparison between 3 and 2. So 2 is smaller, we add 2 here. To an inversion count we will add 0. Then we have 3 and 5. Okay, now 3 is smaller than 5. Then what we are going to do, we are going to put a 3 here and we are going to add 1 here, because we have one element which is greater than equal to 5, that is 5 itself. And finally this array is finished, we will put a 5 here. So what we'll get, we will get 3 cross inversions. Okay, so what is going to be your final answer? Your final answer is going to be nothing but the number of inversions in the left part, okay, the number of inversions in the right part, plus the number of cross inversions. In this case, the left part has one inversion, the right part has one inversion, and the combined part has 3 more inversions. So it becomes 1 plus 1 plus 3. That is going to be. So you can see you can adopt a DNC algorithm, something like merge sort, to solve this problem, and this now can be solved in order of n log n time, because we are doing something which is exactly same as merge sort. So in the next video we will see the implementation of this inversion count method. Hi everyone, so now we will be making some changes to the merge sort function so that it works fine for the inversion count problem. Okay, so let us see what changes we need to make. So maybe if you want, we can do some makeup. We can just call this function as inversion count. Okay, but it is actually merge sort underlying the code. Okay, so yeah, mid, we calculate mid. We will calculate the inversions in the left part. So maybe I call this as count C1. We calculate the inversions in the right part. We call it as C2. The return type should be int. We also need to calculate the cross inversions. Let's call it as CI. And finally we need to return the total inversions, that is C1 plus C2 plus CI. So that is one thing we need to do. Another thing is, while doing merge, we said when we copy the element from the right, okay, we saw this example where we had maybe 0, 3, 5, and maybe we have 1, 2, 10 and 12 here. So when we are comparing these elements, when we take the element from the left, we don't add anything to our inversion, and we said okay, but if we compare 3 and 1, we see 1 is less than 3, or we can say 3 is greater than 1, and it is coming before 1. And similarly, all elements which are after 3, these elements, they will also form an inversion with 1. So we'll have inversion like 3 comma 1, 5 comma 1. For to handle this thing, because we are going to put a 1 here, right? And there won't be a case when we would be comparing 1 with 5. So what we need to do, we need to increase the effective count by a factor of 2. So how do we calculate this thing? So we know this index is mid, this index is currently I. So we say okay, if array of j, yeah, so in this case, right, in this case we need to say, let's take a variable count that is initially 0, and you increment count by a factor of mid minus. Now how many elements you have from I to mid? Okay, so you have mid minus I plus 1 elements. Okay, this is, you can easily verify. So this we need to increment here. Okay, so these are the two changes we need to make. So I hope this thing is clear. Okay, so we are basically counting these elements when we are copying an element from the right and we are putting inside in the temp array. So this is basically the temp array. We are putting a 1 here, and we need to increment the count by a factor of 2. And while doing this, we'll maintain a count variable that is initialized to 0. And once this entire loop is complete, we will return the value of count. So we need to change this to int. We need to say int count is 0, and here we can say count plus equals what, mid minus, that is m minus I plus 1. And finally from this function we can return count. That's it. And here we don't need to print the sorted array. We can say cout. The function name is now inversion count, and we make this call. And here also, instead of merge sort, we can say inversion count, and that's it. Okay, so one more thing, in the base case we can return 0, and yes. Okay, so for this array I should get 5 inversions, and you can see we are getting 5 inversions. Okay, so that's all for this video, and I hope you understood this problem. Thank you.
Hello everyone, welcome to this lecture about ternary search. Again, ternary search is a divide and conquer algorithm. I would like you to know about this because it comes in handy at those places where binary search is not usable, right? So as you can see here, I have a let's call it a function or maybe a parabola, right? A half of it. So where will the ternary search come in use, right? So let's say you have an array, and array contains an elements in this order, right? That means let me name it like this: 1 3 5 7 9, and then let's say it goes down, right? 8 6 4 2 and 0. Cool. So let's say this is the array, and here what I can see is that yes, there is exactly one maxima in the array, right? This is a maxima, right? So it's not like this, like there are many maximas or minimas, right? So here we can see that there is only one maxima, and I have to find this maxima. Like I have to spot that number which contains the maximum element, right? But the thing that I can see is the observant, the property that there the property where the ternary search will be useful is that it should only contain one maxima, right? Only once. I have to just find that location where it is, right? So this is an example of an array where this is possible, but then this can be any other parabola too, right? I have some examples of parabola also. Let's say, okay, examples will come in later, but this can be any function, right? Not just an array of integers, right? So there are many functions in which what you will get is you will get a particular maxima or minima in a certain range, and you have to find that minimum value. Right, for which x will I get maximum of this function or minimum of this function, right? And that's a very important question, right? So all those types of problems regarding maximas and minimas, where we have to find a particular value of x for which this function will give me a maxima, and what is the maximum value, right? That can be easily found using ternary search. Let's see how we can do this, right? So I have taken these three examples, as you can see. So in all these three examples there are three different things, right? That means uh let me okay, so let's start by naming the left part as left, and let's call it right. So we'll do very similar things to binary search, but we'll just divide the whole range into three different parts, right? So let's call it mid 1, and let's call it mid 2, right? So what is mid 1 here? Okay, let me name all of them and then we can continue. Left, mid 1, mid 2, and right. Cool. And similarly for this, left, mid 1, mid 2, and right. Cool. I hope this makes sense. And now let's understand what is mid 1, mid 2, and what are all these things, right? So we have a range just like in binary search, and we are dividing into three parts, three equal parts. So here mid 1 can be is left plus, and if you divide this range, that is right minus left by 3, right? So I'm just taking one portion of it and adding into the left part. So this becomes 3 left minus left plus right by 3, which is nothing but 2 left plus right by 3. Similarly, if you do the same calculation for mid 2, what we'll get is we'll get left plus um right minus left by 3 into 2, right? So we are adding two partitions after left. So this will give you left plus 2 right by 3, right? So earlier what we had is 2 left plus right by 3. Now we have is left plus 2 right by 3. This is normal mathematics, and I'm dividing a range into three different parts. So what is the property that I can observe here if I divide a range into three parts, right? So why have I taken these three different examples? Because these are the only three cases which are possible, right, for a particular maxima. Because there is a whole range, there is a maxima somewhere in middle, and that maxima can either lie on the left partition or on the middle partition or on the rightmost partition, all these three partitions, right? So yeah, now let's understand how does ternary search work, right? So let's figure out few things here. The first thing that we can notice is, let's consider this case, which is um that the maxima is on the leftmost partition, right? So just like binary search, what we will do is we will simply reject one particular side, right? So we have three partitions, so we'll just simply reject one partition. We'll say that okay, maxima cannot lie in this partition. That means just let's just think it over. Okay, so I have okay, I think I will be giving it more space. Right? So I hope this calculation of mid 1 and mid 2 is very clear. We'll be using that calculation in the coding part. Cool. Now let's call this f of 1. Cool, which is mid 1, and this is f of 2, which is mid 2, right? So here I'm just saying that f of 1 is equals to f of mid 1. What is f of something? The value of it at a certain point, right? And if it's an array, it can be ai, basically nothing else, right? So just don't get confused. This is the value f1, this is the value f2, right? And for example, if I have a parabola, let's say y equals to minus x square plus 4x, right? That means if I have some x, I have f of x is equals to y, right? So f of x is equals to this particular y value. So don't get confused, right? And if it's an array, then it is nothing but a of mid 1 fx. Cool. So yeah, now we just have to look at the values, that at this particular location I have this particular value, and at this x I have this value. That means I have an increasing function over this particular range. So if I have an increasing function over this particular range, that means maxima will lie somewhere on the left of mid 2. I hope this makes sense, and this is very important, right? So if I have an increasing function from mid 2 to mid 1 and I'm increasing, right, that means maxima should lie somewhere there. Otherwise, if maximum would have been somewhere elsewhere, then we would not have got this increasing line, right? That means what I can do is I can make my new range equal to left to mid one. This is important, right? So I'm not selecting one partition, I'm actually rejecting one partition, right? So it's not like if I have three partitions, I select one partition and then again I divide into three partitions and select one partition. No, I'm selecting, I have a range, I divide into three parts, I'm selecting two parts out of it, that okay, in these two parts maxima can lie, right? And I'm rejecting one part from it. So basically, if I have left and right initially, now what does it becomes? So left is equal to left because that's the new range, right? And right becomes mid 2. And this is which case? When f of mid 1 is greater than f of mid 2. Cool. So that was the first case we observed. Now let's come to the second case. This is the second case. In the second case, what we can see, we have an increasing slope this way. That means if I have an increasing slope on the right hand side and I want to find the maxima, that means the maxima will lie on the right of mid 1, because to the right of mid 1 it is increasing, right? And if it is increasing on the right of mid 1, that means it has to lie on the right hand side, it cannot lie on the left side, right? So some of you might be wondering that why am I considering the middle portion, right? So let me give you an example, a good example. Oh, okay, that will be cleared out in the next part only, okay, in the third example then. So right now what I have is yeah, so what is my new range? This, right? So similarly as binary search, I'm just dividing the range. So here my left is equal to mid 1 and my right is equals to right itself. Cool. So this is the second case when f of mid 1 is less than f of mid 2. And what if f of mid 1 is equal to f of mid 2? For example, let's say they are equal. Of course they don't look equal, but let's say they are equal. What happens if they are equal? Then we can take any, right? We can take this or we can take this. What does it mean? If both of these particular points are equals, that means it lies somewhere in the middle, right? So we can take any, right? Or we can make a third case and take just one partition, but that won't matter, right? So what we can do is, if it is equal, f of mid 1 is equal to f of mid 2, then we can simply say that okay, make left equal to mid 1 and leave right as it is, or you can also make right equal to mid 2, right? But let's leave right as it is, okay? These are the three cases that I have got, right? So some of you might be wondering that okay, in this case, in the second case, I have seen that the maxima lie on the third partition, but why am I including the second one? So for this I have a very good example for you. Okay, these are other examples. Yeah, so let's say this was my range and this is the value of, let me divide into three parts first. Yeah, and what was the second example? That mid 1 is less than mid 2, right? Let's say this is mid 1 and this is mid 2. Yeah, and now let me join this, right? So as you can see, mid 1 is less than mid 2, right? So I cannot always say that if mid 1 is less than mid 2, then okay, only take the third partition. I hope you got my point. I cannot always take the third partition, because here also we can see that f of mid 1 is less than f of mid 2, right? And if I take the third partition over here, then it will not give me a right answer. Why will it not give me a right answer? Because the maxima is not in the third partition, right? It is in the second partition. So when f of mid 1 is less than f of mid 2, then there is only one thing that I know, that it lies on the right of mid 1. Cool. So if it lies on the right of mid 1 and I already know it lies on the left of right, then that means the new range is mid 1 to right. I hope you got my point, right? That means if f of mid 1 is less than f of mid 2, it's not always this case, right? So this is a case where you can remember how to apply this. How does ternary research work? Just to understand, right? But it's not always this as a case. This can also be a case, right? When f of mid 1 is less than f of mid 2, but the maxima is in the middle portion, right? But you cannot make a case when maxima will be on the left side and this condition holds. There won't be any case, right? So that's my whole point, because if maxima is here, that means after this it is decreasing, right? That means f of mid 1 can never be less than f of mid 2. Cool. So I hope you understood ternary search. This is used to find a maxima or a minima. So similarly, what you can do is you can do the same for minima and try to generalize it yourself. It will be just opposite of the maxima, right? And similarly, if you get this question anywhere that you have an array and it's at increasing and decreasing array, that means it's mountain type array. Then find the middle part or the highest part. Sorry, find the maximum value in that array in, let's say, log of n time or less, right? So you can use this algorithm, right? Now let's understand what is the total complexity of this. So initially we have a range of length n, right? Let's say left to right is n, let's say. Cool. So let's say the range is n. After this, what's happening? The range becomes 2n by 3, right? It's not becoming 1n by 3 because we are removing 1 by 3 of it. The range is still 2n by 3. Then it again becomes 2 into 2n by 3, which is 2 is okay, 2 by 3 square by n, right? Again 2 by 3 cube by n and so on. So this is the function, right? So in binary search, what was happening? N by 2, n by 4, n by 8, right? But in this case, the range is divided not into half but into 2 by 3 of it, right? So there will be a time when this will become the exact value we need. Let's say it is equal to 1 and it took k steps. Then you can simply take log both sides and do the formality. Cool. So the what will the complexity of this algorithm? So for binary search we have n, then n was multiplied by 1 by 2, then again 1 by 2, right? So in that case what we got is log base 2 n, right? In this case what we'll get is log base 3 by 2 n. I hope this makes sense. Cool. Why 3 by 2? Why not 2 by 3? Because in you can take log both sides and see it yourself, okay? Yeah. Or you can relate it to binary search in some way. I hope you got this. How does ternary search work? When to take which partition? So in the next tutorial, in the next video, what I'll do is I'll simply code ternary search. And the here we have some examples of parabolas. I just taken examples directly from mathematics. Also you can take some arrays and find maxima and minima in that array. You can do that too. But I've just taken some examples here, and what we'll do is we'll find some certain values of x. For example, this y equals to minus x square plus 4x, right? Find that value of x where you'll get the maxima, right? So let's solve this problem using code and ternary search. Cool. Thank you everyone. See you in the next part. Right, welcome back. Let's start to code. And okay, so to code ternary search, it is very similar to binary search. So first of all, let me take a huge range and let me call it double, right? So double left, which is, let's call it minus 100, because we know the range should be correct, right? Initial range. So let's say right is equals to 100, right? So what I'll do is I'll simply say while left and okay. So here comes a precision problem, right? So what I'll do is, let's say I want to find out answer till 1 precision, right? After decimal 1 precision. What I'll say is simply, then I'll say if right minus left, if it is greater than 0.1 or let's say 0.01, then perform the following operations. That means left and right are very far placed right now, and soon when the ternary search happen, they will start to come closer to each other, and you know uh, try to minimize that gap of that range where the answer is, right? And there will be a certain time when both right and left will have the same decimal value just after one decimal point. If they'll have the same value after one decimal point, the algorithm will break, then while loop will break. Cool. So let's find out mid one. So mid one was equal to, as I already described, it was equals to 2 into left divided by 3, sorry 2 into left, yeah, 2 into left plus right by 3. And what is mid 2? Mid 2 was equal to left plus 2 into right by 3, right? So these are mid 1 and mid 2, and what I need to find is, I need to find if, let's say, f of x, let's call it f of x, right? So x here is mid 1, right? So if f of mid 1 is less than f of mid 2, the value at mid 1 and mid 2, right? Then what will we do? Let's come back. If f of mid 1 is less than f of mid 2, we'll just make left equals to mid 1, make left equals to mid 1, right? And right will remain as it is. Otherwise, make right equals to mid 2. I hope this makes sense. So after this, what will happen? Left and right will have the same precision till one decimal point, right? And now we have to find out what is f of x. So let's write a function which will return me a double f, right? And it will take a double called x. And let's find out this for just a second. Yeah, let's find out this for this particular parabola, which is minus x square plus 4x, right? So let's take double y is equals to minus x square, x into x plus 4 into x, right? Let me just take, right? And this is, and it will simply return me y, right? Let's build this. Okay, sorry, it's not left, it is not lf. I generally use lf, so that's why it is. Yeah, now what we have got is, we have seen that this while loop only works till when right minus left is, greater than 0.01. But when it subtracts this, then it becomes less than or even equal to 0.01, right? So for this, what we can do is, we can increase my precision, right? So if I want it to be same for 5 decimal places, then we can have 5 zeros, right? Let's build it. Yeah, so I here you can see both left and right is equals to 2, right? And what if the answer is in decimal? Let's say 3x, right? So the answer should be exactly half of it, right? So here you can see we have got 1.5 and 1.5. 1.5 is that value of x where we have the maxima, right? Let's call it 3.45678, and here you will see exactly the half of it, right? So it is 1.72839, and if I want to improve my precision, I'll simply add 2 more zeros, right? Because see, the answer stops here. That's why even after adding precision, I'm not getting any change in the answer, right? What if I add some random values there? Let's see. Okay, so here I got 72812, right? And let me add some precision values. Okay, so I think the problem is in printing. Let me print the decimal till maybe 10 places, right? So I hope you know this. How do we print double values till some certain places? So this will print the decimal till 10 places, right? So here you can see it is 1.72811 and whatever it is, right? And so on, right? And it will keep on changing accordingly, right? If you want to print it let's say 15 places, just do it 15, just make precision 15 and see out it. Cool. I hope ternary search is very clear to you, and you can try the ternary search code yourself on this example, minus x square minus 2x plus 3, and you'll see you'll get a maxima on -1, right? This is -1, and here you will see the maxima, right? So it is also a very famous interview problem, that you have one maxima and the array is increasing and then decreasing, but you don't know where it is. Then how will you actually find it in less than O of n, right? So this is very less than O of n, right? It comes in log base to the power log base 2 by 3. Cool. So thank you everyone. I hope you understood ternary search, and I want you to practice some problems regarding this. It will not always be some arrays or some mathematical functions. Just like binary search, it can be aggressive cows, or painter's partition problem and book allocation problem, right? So similarly, all those types of problems can be converted to ternary search. Cool. So thank you everyone, and see you in the next part.